Hi everyone, this is Lutz and today we're going to talk about these little friends here, the so-called servo. It's a special kind of motor and you can use it if you want to position your device. And this one is really practical because you can directly set a position where you want to drive the shaft from your motor and you don't have to build another positioning sensor. But there are a lot of challenges to make a good control from a Raspberry. And this is where we're going to talk about today. I will give you an introduction how to calculate what servo you need, how the electrical parameters are you have to consider if you want to control it with a Raspberry. And then we will talk about the software part, and at last I give you a sample, a practical example where you can see what you can do with a servo motor. So let's start with the mechanical part. The first thing you always have to consider if you're choosing a motor for your project, it's the question how strong will be the motor you need. And for this there's a basic calculation for the torque of the motor. And this one is corresponding to the torque you find in the datasheet for your servo motor or for something else. And a second part, you need to know how fast it will be. Normally for a normal motor this is given in turns per minute, but for a servo motor this is given as a speed of the angle. So this is what we see here. And now there's a little trick inside. This value gives you the indication about how heavy things could be if you put them in a 90-degree angle to your shaft of your motor. And this is only the basic physics aspect, so this is just giving you the information of the weight of the load you can use, but it's not correlated with a change of the position of the load. So there's no corresponding information inside of the speed, and this is what we need to calculate before we know how big our servo needs to be, because that small one is not made for heavy loads and 1.8 kilo is quite a lot. So as first we have a look into the basic of that formula or of the value. And it's giving you the information that you can use 1.8 kilo in a distance from around 1 centimeter to the shaft of the motor, in the assumption that your weight is exactly in 90 degrees for your motor. And if you now change the distance, you can use the half of the weight. So we want now to make a new step and have a look what is happening if we want to move the load, and then we will calculate what is coming out. So what do we have to do now if we want to calculate the dynamic load we can use for our application? The first thing, we have to calculate the distance our load will make when we make a change of the position of the shaft. So what we do is that we calculate the movement of the angle at the end of the angle. So what we do is that we use the formula you know from math from the school. It's just the formula for the length of a circle. So this will be added by the fact that we just change it by 60 degrees, and then we give it the distance that we will use for our load. In that case it's quite easy, it's 1 centimeter because it's just 2 times p, and that factor is more or less the same, and then you just have the length which you are away from your shaft. And with this you can calculate the speed which your load will do. In that case this is just 1 centimeter and it needs 0.1 second to make that movement. And with this information you can calculate the acceleration of your load. And this is here the formula we will use. And the factor 2 is coming from the fact that we assume that at first we accelerate the load and then it comes to an end position. So what the speed says here is that it's an average, but we don't have a linear speed, we will have an acceleration and a deceleration. And that's the reason why we have to take this with a factor 2. And then we get out that we have 2 meters divided by a square second. And then we calculate from the value we have from the datasheet the so-called SE unit, because this is what we always need if we are making calculations. Always make sure that you're using that kind of units, otherwise it will be misleading. The numbers you will get out are probably wrong because your units are not matching to the formula you have. So always make sure that you're using SE units if you want to calculate something. And with the recalculation, we can just calculate the impact of our acceleration. So what I did is that I take the available force or the available torque I can get out of my motor and divided that by the length of the load and the acceleration I have. So this is more or less that formula, just in another order. And then we will get out that we have 1.4 kilogram we can use in that mode. So this seems to be a lot, but what is happening now if I make the distance a bit longer than I had in the initial example? So let's take around 10 centimeters and we will do the whole calculation again. And then we will see that we will double the acceleration. Okay, that's quite fine. It stays with the same available torque because it's quite the same what I have from the datasheet. And then we will see that we have the distance here, and the distance is also going inside of the acceleration part of the formula. So we call this is a potential change. So this is more than just a linear change, and we see that we have only 60 grams available as a weight on the load from the servo motor. So this is what I wanted to show you. If you choose your motor, be sure that you know the distance you will have and the speed you will have on your load. For sure, this is not a really exact way because you have to make sure that your load will be a bit slower because on the weight all informations you get on a data sheet are normally not that accurate for a movement. This is always a maximum value or something like this, but it gives you a good feeling if your motor is strong enough for that what you wanted to do. So this I wanted to show you because I often read and I often hear that motors are dying and people don't understand why. And basically this is one of the problems. People don't think about the force you have for accelerating your load. Next thing is the electrical part of your motor, and for this we are looking for the current at first. So we are just looking what current consumption we have, and this we can figure out in a datasheet. Here's coming a typical problem. The datasheets are mostly not complete. If you find something for a cheap part, it's mostly the problem that some parts are not there. So this is taken out of another datasheet than the one before, but here I get some information about it, and we see that it will need 360 milliamps. And now you have to ensure that your system is strong enough to carry that additional load to your Raspberry Pi load. So the first problem, what is mostly occurring, is that you have to less current ability from your power supply. And for this you have to make sure that your power supply is strong enough. If it's not, it will be getting a reset to your Raspberry and the motor will stop working. The second problem what could be happen is that your power supply is strong enough, but the resistance you have in your wires and you have in your copper on your PCB and so on is so high that you get a voltage drop and your Raspberry is not working. The problem is it came to the same conclusion at the end. Your Raspberry will run into a reset, and if you don't have an oscilloscope, it's hard to figure out what is the problem. So always make sure that you have the wires you need, or you make a more stable power supply architecture. I will show you on the next slides how this could be. But firstly, we want to have another look for another signal, because as you saw on the servo, we have 3 wires, and the reason for the third wire is that the third wire will indicate the servo the position he should reach at the end. So how is it working? Now we have a PWM signal here, and the PWM signal is 20 milliseconds long, and the duty time is between 1 millisecond and 2 milliseconds. And this is a bit different in every servo motor you will use, but in that one here it's between that range. Some are between 500 microseconds and 2.5 microseconds, so make sure before you run your application in which range you have to adapt that pulse. And the zero position in that case is 1.5 milliseconds pulse, and 90 degree is 2 milliseconds. And that's what we need to ensure in our software, that this pulse is correlating to the position we want to go. Where mainly the most problems are coming from, that people don't understand how to set up the Raspberry in the right way to make sure that those timings are correct. Because if you don't do this, you get into a really problem, because you get all the time a jittering. And this is really annoying and not helping if you want to stand or to program a position. And let's have a quick talk about the power supply architecture we can use. This is more or less the standard application you will use on your Raspberry if you have a small servo motor. You're just connecting your power supply and your ground directly to the pin header, and then you will use an additional GPIO pin to control that servo motor. But if you have stronger motors, or if you have another application, maybe it's better if you just use something like this. So in this application we use a battery to supply our servo directly, and we will use a step-down converter to ensure that we have the correct voltage we need to supply our Raspberry. So we make a bit of decoupling between both. And this is quite useful, because here you have a high power path and then you have a step-down converter, and you get a clean output voltage, and that helps a lot to stabilize your voltage on your Raspberry. Even if you have more motors or something like other loads where you have a higher current flow, make sure that you have a decoupling between the power supply and your Raspberry. So for our software part, we will use GPIO 0 running on a Raspberry with a Python environment, or in a Python programmable in a Python language. So if you did not already install it, just type in sudo apt install Pi3 minus GPIO 0, or you can also use a pip command if you want to use it like this, then it's also able to install. The GPIO 0 library gives you a lot of opportunities for using your GPIOs on your Raspberry. So there are a lot of applications and runnable source code that you can use directly to run your Raspberry. In our case, we want to use an output device, and the practical thing is that the server is already defined, so we don't need to do anything. So we will keep that as close as the tutorial. But here's one problem: they are not using the fast pin factory. So this gives us a problem that we will have to deal with a lot of jitter, and I don't like to have a hard resolution where I have the whole time a jitter inside and it's making blah 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 blah. That's not good for positioning anything. So we will also activate the correct pin factory. And here I just want to show you there are a lot of things where you can directly work on your servo motor and control it. So use that one if you want to do something with a servo motor. It's quite easy. So what we need to do now on our Raspberry, I also prepared here some Python code. But the first thing I want to show you is that we need to enable the pin factory service. Otherwise we will run into a problem because the software code I would show you is not working without this. So we go to the system control and then we enable the Pi GPIO service. This is already prepared if you install GPIO 0. So just run that, and after a reboot this will be automatically set. So it's right helpful to just say enable and not say start like you do it in a service you want to run once. So always use enable if you want it to be, or if you want to have it available after a restart. So yeah, that's what you need to do for your pin factory. And then I will quickly show you the code I'm using here. So we import from the GPIO 0, we import the servo. So this is what I already showed to you. And then we are just using from time the sleep mode. You can do this also in a different way, but I like this. It's quite easy to read and to understand. And next thing is that we import the pin factory. So we also include from GPIO 0 the pin factory, and then we define the factory as GPIO 0 as GPIO factory. The reason why we do this, as I mentioned before, the standard GPIO control is too slow to run exact the timing you need to position your servo. Otherwise you get this jitter, and this we want to avoid. So make sure that you use the correct pin factory. And then we initiate an object with a servo, and this is, in my case, this is here running on pin 14. So if you watch the video completely before, you see where I'm connecting the output control for the servo motor. So do this as well, and then it's pin 14. If you are running into an issue because you don't know where your pins are, there's a small trick I can show you. I like this a lot. It's just that you type in pin out in the command, and then you get this information here, which shows you directly which pin is set. So you see this here, and then you can directly watch what kind of GPIO you're using. I find this quite helpful. So if you need more information, you also can put this, you can click on this one, but it's not necessary here. So the next thing we do is we set the minimum pulse width. And in my case, this servo motor is starting at 500 microseconds, and the maximum pulse range is 2.5 milliseconds. So this is necessary to set correct. And then we give it the new pin factory. So what I do as next is that I just step through the whole angle range I have with a step size of 60 degrees. And this I will give the servo as a value, and this is just calculated here. And afterwards I sleep for 1 second. So I think that's quite easy to start with, and yeah. So we see that's working without a jitter, so that's quite practical. And as next thing, we will have a look into a practical example of what we can do with it. So let us come to a better practical example of what we can do with a servo motor. So I know this is not really beautiful, but it's working, and for a quick example, I hope it's enough. So what I did is that I just collect the box from the X and just put my Raspberry inside and fixed my webcam inside of the box. Here I have a connection to the motor and the power supply. What I do now is that I have here the opportunity to connect this with my servo motor, and now I'm able to turn it over the Raspberry Pi script. So what I can do now is that I can arrange the angle where my camera should show something. And just for you to remember, now you see the reason why it's important to know how heavy my load could be, because here I'm having a much bigger distance than I have here inside. So this is quite a lot more, and you should know how heavy the load could be you're using on your servo motor. So now let's go back to the desktop and I show you how it's looking if it's moving. So let's go back. So now we are back, and what you see here is now my stream which I received from the Raspberry camera. And if you want to know how to set this one up, you can find it in the video I will give you on top. And on the right side you see again our script. I just changed here the angle where we want to rotate, and then I give you with my smartphone the view of the box, how it's rotating. So let's start our script and see what's happening. So as you see, it's directly starting to move the whole box, and after a short time it's just changing again the position. This is based on the sleep time we have here. And now you see by the movement of the box how important it is to have some idea about the weight of the box you're using. And yeah, that was what I wanted to show you as a practical example. I hope you enjoyed the video and learned a lot about servo motors and how to use them on a Raspberry Pi. And I hope to see you next time. So goodbye.